Module 8, Lecture A, Understanding Errors. By the end of this lecture, you will be able to differentiate between syntax, runtime, and logical errors in Python programs, interpret Python error messages and tracebacks to identify where an error occurred, and fix common beginner mistakes that lead to typical Python errors. Python error types. Syntax errors explained. Syntax errors in Python happen when the interpreter cannot even begin running your program because the code breaks the language's rules. They are like sentences with broken grammar, where required keywords or symbols are missing or misused. When this occurs, Python stops immediately and reports an error before any of your code runs. This is different from runtime errors, which occur only after the code has successfully started executing. Syntax errors in Python usually come from problems with punctuation, colons, parentheses, quotation marks, or indentation. For example, leaving out a colon after a line that starts a loop or conditional, or forgetting to close a parenthesis or a quote will cause the interpreter to stop and report an error. Even small issues like an extra character, a misspelled keyword, or misaligned indentation can trigger these errors. In all these cases, Python cannot correctly understand the structure of your code, so it treats the program as malformed and refuses to run it. Syntax errors are often the first challenge in programming, so it is important to learn to recognize and fix them early. Python helps by showing an error message and pointing to a location in your code, which may not be the exact problem, but indicates where the confusion begins. Over time, you will notice patterns, such as an unexpected end of file hinting at missing a bracket or quote, or invalid syntax near a keyword suggesting a missing colon. By carefully reading these messages and comparing them to what Python expects, you can quickly find and correct syntax errors before moving on to more complex debugging. Python code, syntax errors explained. In this section, we will demonstrate Python syntax errors using simple, safe string examples and show how the interpreter reports invalid syntax messages. We will compare incorrect code snippets that trigger these errors with their corrected working versions, so you can clearly see what went wrong and how to fix it. If a required library is missing, we will also briefly show how to install it using the standard package installation command. In this example, we store a line of Python code that contains a syntax error. The line is meant to create a for loop that iterates 3 times, but it leaves out the required colon at the end of the loop header. This missing colon is a common mistake and causes Python to raise a syntax error. The colon is necessary for Python to recognize and define the block of code that belongs to the loop. This description explains a corrected Python for loop that now includes the required colon at the end of the loop header. The loop runs over 3 values and prints each one. The key idea is that the colon marks the beginning of the loop's code block. Without this colon, the loop would not execute properly. We create a variable that stores a line of Python code containing a syntax error. The line tries to assign a string to a variable, but it is missing the closing quotation mark. Because the string is not properly ended, Python will raise a syntax error. We keep this incorrect line so we can see how Python reports the error and later compare it with a corrected version. This statement shows a corrected Python line where a string variable called message is set to the text "Hello Beginner." The quotation marks are properly closed, so the string is complete and valid. Because of this, the code avoids syntax errors related to an unfinished string and can run correctly. In this example, a string is defined to hold a Python command that should print the result of an arithmetic expression, but it contains a syntax error caused by mismatched parentheses. The expression is meant to add 2 and 3, then multiply the result by 4. However, a closing square bracket is used instead of a closing parenthesis. Because of this mismatch, Python cannot parse the command correctly and raises a syntax error when it is executed. This statement is a corrected Python command that prints the result of an arithmetic operation. It fixes the placement of parentheses so they are properly matched, which is important for preserving the intended order of operations. Inside the print function, 2 and 3 are added together, and then that sum is multiplied by 4. This shows the correct syntax for writing arithmetic expressions in Python. The show example function is defined to take 3 inputs: a description, a wrong code sample, and a correct code sample. It is used to demonstrate syntax errors by printing a short explanation of the issue, then showing the incorrect code that would cause the error. After that, it prints the corrected version so learners can see how the code should look to run properly. This structure helps students recognize common syntax mistakes and understand their fixes. This line uses the print function to show a short description of the syntax problem being discussed. It displays the word "problem" followed by a brief explanation of the specific issue. By stating the type of syntax error up front, it makes the purpose of the example clearer. This helps the listener understand the context of the code examples that come next. This line shows the incorrect code that would cause a syntax error in Python. It is used as part of a demonstration to illustrate what happens when Python encounters invalid syntax. By displaying the wrong code, it clearly points out the specific mistake. This makes it easier to understand the correction that comes next. This code displays a corrected version of a previous code snippet that now runs without errors. It uses a print statement to show a label indicating that the code is fixed, followed by the corrected code itself. This makes it easy to compare the original incorrect syntax with the corrected version and understand what was changed. This example uses a helper function to show a common Python syntax error, forgetting the colon at the end of a for loop header. The function first describes the problem, then shows a version of the code that is missing the colon and would cause a syntax error. It then presents a corrected version with the proper colon that runs successfully. Together, these two versions highlight how small syntax details are essential for Python programs to work. This example explains a common Python syntax error caused by leaving a quotation mark unclosed in a text string. A helper function is used to present the problem description and then show two versions of the code. One version contains the error with the missing closing quote, and the other shows the corrected code with the quote properly closed. By comparing these two versions, learners can see how this type of syntax error occurs and how to fix it. This example shows how mismatched parentheses in an arithmetic expression lead to a syntax error. A demonstration function is used to present both the incorrect version, where the parentheses do not match properly, and the corrected version, where they are balanced. By comparing the two, you can see how proper use of parentheses ensures the expression is valid and evaluates as intended. The goal is to highlight a common syntax mistake and how to fix it. This script demonstrates common Python syntax errors and how they appear when reported. It shows incorrect code examples next to their corrected versions, so you can clearly see what went wrong and how to fix it. The issues include missing colons in loop headers, unclosed quotation marks in strings, and mismatched parentheses in expressions. By comparing each faulty snippet with its corrected form, the script helps reinforce proper Python syntax and deepen your understanding of how to avoid these errors. Runtime exceptions. Runtime exceptions are errors that occur while a program is running, even if it passed earlier checks. They depend on the specific data or environment at that moment, so a program might work correctly with some inputs, but fail with others, such as when it receives text instead of a number. Because they only appear under certain conditions, these exceptions can be difficult to predict and require careful thinking about how the program will be used in real situations, not just how it is supposed to work in theory. Runtime exceptions occur when code that is syntactically valid fails while the program is running because of the actual data or conditions at that moment. For example, trying to access the 10th item in a list that only has 5 items, or dividing a total by 0 in a financial app due to a bad input will both cause runtime errors. These cases show that runtime exceptions depend on the current state of data and resources, not on the code structure alone. In real-world programming, many runtime exceptions come from unpredictable external factors, such as unstable networks, misbehaving servers, or unexpected data formats. A program might work correctly when conditions are ideal, but fail when the network drops or when text appears where numbers are expected. These situations show why it is important to anticipate runtime exceptions during software design. By planning for problems with user input, files, and network conditions, you can make your programs handle errors gracefully and either keep working or fail in a controlled way. Python code. Runtime exceptions. In this lesson, we use simple temperature and division examples to show how runtime exceptions can occur, even when the code syntax is correct. These examples highlight that valid code can still fail if the data causes problems, such as dividing by 0 or using invalid values. We then demonstrate how to handle these situations safely by wrapping risky operations in try blocks. Finally, we show how to print clear, friendly messages so the program fails gracefully instead of crashing without explanation. This line is simply a placeholder comment indicating that you could install an external library if needed, but it also clarifies that the existing standard Python libraries are enough for the task. In other words, the code is designed to run in a normal Python environment without requiring any extra packages. It reassures the reader that no additional setup beyond the usual tools is necessary. We create a list of temperature values in Fahrenheit using 5 specific numbers: 72, 68, 75, 70, and 69. This list serves as sample temperature data for the program. Its main purpose is to be used later to show what happens when the code tries to access a position in the list that does not exist. This example helps demonstrate how such an error can cause a runtime exception and why it is important to handle these exceptions properly in Python. The show10th temperature function is meant to print the 10th item in a list, which is the element at index 9, because lists start counting from 0. If the list has fewer than 10 elements, trying to access this position causes an index error. To prevent the program from crashing, the code wraps this access in a try block. If an index error occurs, the except block catches it and prints a message explaining that an index error happened at runtime, along with details about the error. This way, the program can handle short lists gracefully and keep running. This function computes the average miles per trip by dividing the total miles by the number of trips inside a try block. If the division works, it prints the resulting average. If the number of trips is 0, the division fails and raises a ZeroDivisionError. In that case, the function catches the error and prints a message explaining that a division by 0 occurred during runtime. The code first prints the list of stored Fahrenheit temperatures so you can confirm the data being used. It then calls a function that tries to access the 10th temperature in the list, which likely does not exist. This situation is used to show how attempting to reach an invalid index can cause a runtime error. By wrapping this access in a try block, the code catches any index error and prints a friendly message instead of allowing the program to crash. A function is used to calculate the average miles per trip by dividing the total miles by the number of trips. When it is called with 300 miles and 3 trips, the division works correctly and returns 100 miles per trip, which is then printed. When the function is called again with 300 miles but 0 trips, it tries to divide by 0, which is not allowed and would normally cause a runtime error. However, the code uses a try block to catch this ZeroDivisionError and instead prints a clear, friendly message explaining what went wrong, so the program does not crash. This script shows how to handle runtime exceptions so a program does not crash. It first tries to access a list element that does not exist, which raises an index error that is caught and reported with a friendly message. It then computes average miles per trip by dividing total miles by the number of trips, working correctly when the trip count is valid. When the trip count is 0, a division by 0 error occurs, which is also caught and explained. Together, these examples demonstrate how to catch and respond to common errors gracefully while keeping the program running. Logical error patterns. Logical errors are bugs that let your program run but cause it to produce wrong results. They happen when there is a mismatch between what you meant the program to do and what you actually wrote in the code. For example, you might try to compute an average, but divide by the wrong number, or apply a discount to all customers instead of only some. In these cases, the computer faithfully follows your instructions, but not your intentions. And that gap is where logical errors occur. Logical errors often come from wrong assumptions about control flow, conditions, and boundaries. A common example is a loop that accidentally skips the first or last item, or a decision structure that sends certain cases, like age groups, to the wrong outcome. In these situations, the program still runs and may appear correct at first. However, it fails for specific inputs or edge cases that were not originally considered, making these bugs harder to detect. Logical errors often come from misunderstanding the data or operations in a program, such as confusing net and gross values or mixing up units like meters and centimeters. In scientific simulations, applying a transformation twice instead of once can distort results. And in data analysis, incorrect filtering can produce misleading summaries. These mistakes are usually subtle, so you need to compare the program's behavior with the intended outcome. Test with a wide range of inputs and question whether outputs that look correct are actually accurate. Python code, logical error patterns. Use a simple average score example to show how logical errors can appear in code that runs without any visible error messages but still produces the wrong result. Demonstrate that the program may calculate an incorrect average even though it executes successfully. Then compare the faulty logic with a corrected version to make clear how the intended behavior differs from what the buggy implementation actually does. This contrast helps learners see that passing syntax checks is not enough. The logic itself must correctly match the programmer's intention. This line indicates that you could install an extra library if needed, but explains that it is not actually required here. It serves mainly as a placeholder for possible future dependencies in more complex versions of the code. In the current situation, everything is handled using only Python's built-in features, so no additional installation is necessary. We begin with a list of 5 student test scores, each given as a percentage. This list serves as our sample data for exploring how logical errors can occur when calculating averages. By establishing these scores first, we have a clear set of values to use in later calculations and comparisons. In this example, the average is calculated incorrectly by adding the scores and dividing by 4, even though the correct divisor should be the actual number of scores. This creates a logical error in the program. The code still runs without crashing, but it produces a wrong result because the underlying logic is flawed. This shows that a program can be syntactically correct, yet still give incorrect answers if the logic is not carefully designed. To find the average score, first add together all the scores in the list. Then divide this total by the number of scores, which is simply how many items are in the list. Using the correct count of scores as the divisor ensures you get the true average value. In this example, the program calculates an average score using 4 as the divisor instead of the actual number of scores. So it prints an incorrect result. The code runs without crashing or showing any obvious problems, but the output is still wrong. This illustrates a logical error, where the program's logic is flawed, even though it executes successfully. It shows how subtle mistakes in the calculation can lead to incorrect outcomes that may go unnoticed if you only check that the code runs. The code correctly calculates the average of the student's scores by dividing the total of all scores by the number of scores in the list. Using the list length as the divisor ensures the result is the true average. This correct value is then compared with an earlier, incorrect average to reveal the logical mistake in the previous calculation. In this step, we find the difference between the correct average and the incorrect one to show how a small, logical mistake can change the final result. By subtracting the wrong average from the correct average, we measure exactly how large the error is. This emphasizes why it is crucial to use the proper divisor when calculating averages, since even a simple mistake can lead to a noticeably different outcome. The code prints the difference between the correct average and the one computed with a mistake. This shows how a logical error, such as dividing by the wrong value, can change the result without causing any runtime error. By making this difference visible, it emphasizes the need to carefully check the logic behind numerical calculations. This script illustrates a logical error when calculating the average of student scores. It first computes an incorrect average by dividing the total of 5 scores by 4, which produces a wrong result that still runs without any error. Then it correctly calculates the average by dividing the same total by the actual number of scores in the list. By printing both averages and their difference, the script shows how a small mistake in the divisor can lead to incorrect outcomes even though the program appears to work. Understanding tracebacks. Traceback structure. When Python encounters an error it cannot handle, it produces a traceback, which is a record of what the interpreter was doing when the error occurred. It begins with a line announcing the traceback, then lists the sequence of function calls that led to the problem, and ends by naming the error type with a short message. Each entry shows where one part of your code called another, leading back to the exact point of failure. Understanding this structure helps you turn a confusing error message into a clear picture of how your program reached the line that caused the error. A traceback is built from the call stack, which is a series of frames showing each step in the program's execution. Each frame records the file, line number, and function or module that was running at that moment. The frames are ordered from the outermost call, such as the main script, down to the innermost call where the error happened. By reading these frames in order, you can follow the chain of events that led to the error, instead of seeing it as an isolated problem. At the end of a Python traceback, the final line states the specific error type, such as a type error or value error, along with a short message describing what went wrong. This line corresponds to the last frame in the call stack, which shows exactly where the exception occurred in your code. By recognizing the overall pattern of a traceback, with its heading, sequence of frames, and closing error summary, you can more easily read even complex tracebacks and locate the source of the problem. Python code traceback structure. This lesson demonstrates a simple traceback using nested function calls so learners can see how errors are reported. It shows how the call stack is built from the outermost function to the innermost one where the error actually occurs. By examining this structure, beginners learn to match each stack frame with its place in the code. The goal is to help them connect the final summary line of the traceback to the exact location of the error. This line is a placeholder comment reminding you to install any library the code depends on before running it. It marks where you would add a command to install a required package. Its purpose is to ensure all dependencies are present so the script can execute correctly in the current environment. consider a function called convert inches to feet that takes an input value representing inches. Inside this function, the code incorrectly tries to add this numeric inches value to a text string. This mixes a number with a string, which is not allowed and causes a type error. Because of this error, the function never reaches its return statement, so no result is actually produced. The process measurement function is designed to convert a measurement by calling another function that should change 12 inches into feet. However, there is an error inside the conversion function, so the call fails and the conversion never completes. Because of this failure, the line that would print the message stating that the feet result equals the conversion outcome is never reached or executed. The main program function simply starts the sequence of function calls for processing a measurement. It first prints a message to indicate that measurement processing is beginning, which helps track the program's flow. Then, it calls the measurement processing function, which triggers a chain of nested calls that eventually produces an error. The purpose is to show how an error can propagate through these calls, while the main program itself does not handle the error and leaves that responsibility to other parts of the code. We use the traceback module to handle and format error information in our program. The main program runs inside a try block and triggers a series of nested function calls. If any exception occurs during these calls, it is caught by the except block. There, we first print a custom message to warn that a formatted traceback is coming. We then use the traceback module to print detailed exception information, including the call stack, so we can see where the error happened in the code. This script is designed to show how a Python traceback works by deliberately causing an error. The main function prints a message, calls a processing function, and that function calls another one that tries to add a number to a string, which triggers a type error. The error is caught in a try-except block, and the script prints the traceback. This traceback lists the chain of function calls from the main function down to the exact line where the error occurred, helping you see how to trace through nested calls to find the source of a problem. Reading line numbers. When you see a traceback in Python, the most important thing to look at is the line number where the error was found. This number tells you the exact place in the file that triggered the problem and is your main starting point for debugging. A traceback shows a series of function calls including the file, line number, and some context for each one. Even if the real cause is earlier in the code, that reported line gives you a concrete location to begin your investigation. When you see a line number in a Python error message, remember it marks where Python detected the problem, not necessarily where the mistake started. For example, if bad data is passed into a function, the error may appear inside the function rather than at the point where the data was first mishandled. The same idea applies in data analysis, where flawed input might only cause an error once calculations begin. To debug effectively, look at the line in the traceback and also read the surrounding code so you can trace back through the steps and find the true root cause. When your projects grow to include many files and libraries, traceback line numbers help you tell your own code apart from external code. Long tracebacks may show many lines from libraries, but you should focus on the first or last line that refers to one of your files. In a complex app, an error might pass through several framework layers before reaching your code, so look for the first file name you recognize. By practicing this, you will get better at quickly spotting the most relevant lines and fixing issues efficiently in your own code. Python code, reading line numbers. In this lesson, we will show how traceback line numbers help you locate errors in your code. We will use a simple chain of function calls that deliberately triggers an error so you can see exactly where it occurs. By walking through the traceback, you will learn how to match file names and line numbers to the corresponding places in your code. No special libraries are required beyond the standard Python tools. We use the traceback module to get detailed information about exceptions in our code. It shows exactly where an error happened, including the file name and line number. This makes it much easier to trace the source of a problem and debug the program effectively. This function calculates miles per gallon by dividing the miles driven by the gallons of fuel used. It takes the miles and the gallons as inputs and returns their quotient as a measure of fuel efficiency. However, if the gallons value is 0, the division cannot be performed and will cause a division by zero error. The example is meant to illustrate this potential error scenario. This function defines a process called trip summary that intentionally produces an error. It sets the distance driven to 120 miles and the fuel used to 0 gallons. It then calls a separate function that calculates miles per gallon using these values. Because the fuel value is 0, the calculation attempts to divide by 0, which causes an exception. The example is designed to demonstrate this kind of error. We call a function that calculates the trip summary and expect it to return a result, such as miles per gallon. Because this function is intentionally written to cause an error, we place the call inside a try block, so the program can handle problems gracefully. If an exception occurs, an except block runs and prints a message that an error happened. To better understand the issue, we then use the traceback module to print detailed information about where and why the error occurred in the code. This script shows how to trace errors in Python using the traceback module. It defines a function to calculate miles per gallon, then deliberately causes a division by 0 by using 0 gallons. When the script runs, this triggers an exception, which is caught by a try-except block. The code then prints a formatted traceback that shows exactly where the error occurred, including the relevant line numbers and file names. This helps programmers clearly see the connection between the error message and the specific location in their code. Reading error messages. When reading a Python traceback, focus on the final line because it tells you the error type and a short message about what went wrong. The error type, such as a name error or type error, identifies the general category of the problem. The message then describes the specific situation, like an undefined variable or an operation that is not allowed. By carefully interpreting this message and connecting it to what your program is trying to do, you can usually figure out the underlying mistake. When you see a Python error message, treat it as a useful clue rather than confusing jargon. These messages usually point to the exact value variable, or operation that caused the problem, such as combining incompatible objects or using an invalid index. For example, an index out of range message means the code tried to access a position that does not exist, and a missing key message means a dictionary lookup failed. By carefully reading and interpreting these messages, you can understand what your program attempted to do, why it failed, and how to fix the issue more effectively. Learning to read error messages is an important part of becoming a proficient programmer. At first, phrases like unsupported operand type or object is not callable may seem confusing, but over time, you will link them to common situations, such as using incompatible data in arithmetic or trying to use data as if it were a function. When you see an unfamiliar error, rephrase it in your own words and connect it to what your program is trying to do, like cleaning data or automating a task. This habit turns error messages from something mysterious into concise explanations of what the interpreter expected versus what actually happened, helping you adjust your understanding and fix the problem. Python code. Reading error messages. In this lesson, we will focus on reading Python error messages clearly and calmly so beginners can understand what went wrong in their code. We will present the error type names together with simple, friendly explanations and connect each message to a real code situation. This will help learners see that errors are normal and informative, not something to fear. No external libraries are required for this basic demonstration, though you can install any needed library with the usual package manager if necessary. We first create a list that stores several daily temperature values, measured in Fahrenheit, which can later be used to analyze or visualize temperature trends. We then define a dictionary that links simple city names to their population counts. This dictionary provides a convenient way to store population data and quickly look up or process the population for each city. We create a small set of example error messages as plain text to represent common Python mistakes. One message shows a name error caused by a misspelled variable name. Another shows a type error from trying to add values of incompatible types, such as an integer and a string. A third example is an index error that occurs when accessing a list position that does not exist. The final message is a key error, which happens when trying to use a dictionary key that was never stored. This material explains several common Python error messages in simple terms. One error happens when a variable name is misspelled, so Python does not recognize it. Another occurs when you try to combine numbers with text, which are incompatible types. A third error appears when you access a list position that does not exist. Finally, there is an error that occurs when you try to use a dictionary key that was never added to the dictionary. The code begins by printing a short header that introduces the demonstration. This header explains that the upcoming output will focus on reading Python error messages and translating them into plain English. By doing this, it prepares the audience for what they are about to see and clarifies the purpose of the examples that follow. Overall, it sets the context so learners know the demonstration is about understanding error messages more clearly. The code loops through pairs of error messages and their explanations. For each pair, it first shows the error exactly as Python would display it. so the listener can hear the raw output. It then follows with a clear, friendly explanation that describes the likely cause of the error in plain language. This connects the technical error message to an understandable description of what went wrong. This script demonstrates how to understand Python error messages by pairing them with clear, friendly explanations. It begins with a short introduction, then goes through several common errors, including name errors from misspelled variables, type errors from combining incompatible data types, index errors from accessing positions that do not exist in a list, and key errors from missing entries in a dictionary. For each case, it shows the kind of message Python would display, and then explains in plain language what likely went wrong. By connecting each error message to a simple explanation, the script makes it easier for programmers to recognize problems and debug their code more confidently. Frequent Python mistakes. Indentation pitfalls. In Python, indentation is a fundamental part of the language, not just a visual style choice. Errors like unexpected indents occur when the structure of your code does not match what Python expects. This often happens when people bring habits from languages where indentation is optional. Python uses indentation to show which statements belong inside loops, conditionals, and functions, so even a single misplaced space can change the program's logic or cause it to fail. Indentation problems in Python often come from mixing tabs and spaces, or using different amounts of spacing as code is edited or copied from various sources. The code may look aligned to you, but Python treats these differences as separate indentation levels and can raise errors. Like hidden formatting in a shared document, inconsistent indentation creates confusion. Python's interpreter therefore requires perfectly consistent indentation to correctly group and execute statements. A common indentation mistake happens when you change a loop or conditional, but forget to adjust the indentation of all the code that belongs inside it. In that case, only some of the logic runs under the control structure, while the rest runs outside it and can cause unexpected behavior. To avoid this, treat indentation as a visual map of your program's logic. Make sure every statement that should be part of a block is indented consistently, and update the indentation whenever a control structure begins or ends. Python code. Indentation pitfalls. This lesson focuses on using indentation to clearly control which lines of code run inside a block. You will see how correct indentation keeps related statements grouped together, while misaligned indentation can change a program's behavior in unexpected ways. By treating indentation as a visual map of the program structure, beginners can better understand how the code flows and which parts belong together. This line is simply a placeholder comment indicating that if extra libraries were ever needed, they should be installed. But for this script, the standard libraries are enough. It serves as a reminder to developers to check that all dependencies are available. In this specific case, no additional installations are required beyond what is already included by default. We define a function that takes a temperature in Fahrenheit and checks whether it is below 32 degrees. Inside the function, a conditional statement tests if the temperature is less than this freezing point. If the condition is true, the program prints a warning that the temperature is below freezing and that roads may be icy. This example shows how proper indentation ensures that the warning message is printed only when the condition is met. The code checks whether the temperature in Fahrenheit is at least 32 degrees. If it is, the program prints a message saying the temperature is above freezing. This implies that road conditions are less likely to be icy. The message only appears when the temperature meets or exceeds the freezing point. This example function shows a common indentation mistake in Python. It takes a temperature in Fahrenheit and checks if it is below 32 degrees. If so, it prints a warning that roads may be icy. However, the next message is not indented under the condition, so it runs every time the function is called, no matter the temperature. This demonstrates how incorrect indentation can cause code to behave in unintended ways. We demonstrate correct indentation by first announcing that we are checking a temperature of 25 degrees Fahrenheit, then calling a temperature checking function with that value. The function evaluates whether this temperature is below or above freezing and prints a message about road conditions. Proper indentation ensures that the warning about icy roads is printed only when the temperature is below freezing and not when it is above. This example demonstrates incorrect behavior caused by bad indentation in a temperature checking function. We test it with a temperature of 25 degrees Fahrenheit, which is below freezing, so the function should print a message only in that case. However, because one line is indented incorrectly, the function also prints an extra message every time it runs, no matter what the temperature is. This shows how misaligned indentation can make a program produce unexpected output. This example demonstrates how incorrect indentation can cause a program to behave unexpectedly. We first announce that we are showing incorrect behavior with a temperature of 50 degrees Fahrenheit, then call a temperature checking function that has a misplaced print statement. Because the print statement is not properly indented, the message about roads being icy is printed no matter what temperature is given. This shows that misaligned indentation can make a program ignore its intended conditions and always run certain lines of code. This script shows how indentation affects the behavior of a Python program by comparing two temperature checking functions. In the correctly indented version, the message about icy roads appears only when the temperature is below freezing, and a different message appears when it is at or above freezing. In the incorrect version, a misaligned print statement runs every time, even when it was meant to be conditional. Testing with temperatures like 25 and 50 degrees reveals that the second function always prints an extra line, demonstrating that improper indentation can break the intended control flow of the program. Fixing name errors. Name errors are a frequent source of frustration for new programmers and happen when Python encounters a name it does not recognize, often due to a small typo in a variable or function name. When this occurs, the program cannot respond because the name does not match what has been defined. Learning to notice, understand, and track down these errors is important for writing reliable code. By systematically finding and fixing name errors, you build confidence and fluency in your programming skills. Name errors in Python usually come from simple issues like spelling mistakes, inconsistent capitalization, or using a name before it has been defined. Because Python treats uppercase and lowercase letters as different, a variable defined one way will not match if you later use a different capitalization. Another frequent cause is trying to use a variable or function before Python has processed its definition, such as using a value in a calculation that is only defined later in the code. These problems are especially common in longer programs or interactive sessions where it is easy to lose track of what has already been defined. To fix name errors, carefully read the error message and check that the name is spelled and capitalized correctly. Make sure the name is defined before you use it, and that it is defined in the right scope. Remember that something defined inside a function is not available outside that function. By keeping your naming consistent and reviewing definitions and scope, you can quickly reduce and resolve most name errors. Python code: fixing name errors. This lesson will show common name error mistakes in code and how to fix them. It will focus on problems caused by spelling errors, incorrect capitalization, and using names before they are defined. For each issue, you will see both the failing error message and the corrected version that runs successfully. The goal is to clearly connect each type of mistake with its solution so you can recognize and avoid these errors in your own programs. This line serves as a placeholder to remind you to install any libraries the script needs before running it. It highlights that all required dependencies must be set up so the code can execute correctly. In many scripts, this is used to manage external packages that are not included in the standard Python library. Ensuring these packages are installed helps create the proper environment for the script to function as intended. In this example, we define a function that sets an original price of $50, then tries to compute a discounted price by multiplying it by 0.9. The calculation uses a misspelled version of the original price variable, which causes a name error. This code is placed inside a try block so that when the name error occurs, it is caught by an except block. The program then prints a message explaining that the error was caused by a misspelled name, along with the error details. This illustrates how a simple typo can trigger a name error and how to handle it using a try-except structure. This function sets the original price to $50, then applies a 10% discount by multiplying the price by 0.9 to get the total cost. It then prints this discounted total with a clear label indicating that it is the corrected or fixed version. The goal is to make the final output easy to read and understand. This example shows what happens when code tries to call a helper function before that function is defined. The call is placed inside a try block, and because the function does not yet exist, Python raises a name error. The except block then catches this error and prints a message explaining that the function was undefined. Overall, it demonstrates that using a function before its definition causes an error, and that a try-except structure can handle this situation gracefully. We define a helper function that takes the number of miles driven and estimates fuel use. It assumes the vehicle gets 25 miles per gallon, so it divides the miles driven by 25 to find the gallons used. The function then returns this value rounded to 2 decimal places to give a clear, precise result. In this example, we call a function designed to show a common mistake that causes a name error. Inside the function, a variable name is intentionally misspelled, and when the code tries to use it, the name error occurs. A try except block catches this error and prints a message explaining what went wrong. This demonstrates both how such errors arise and how they can be handled in a controlled way. In this example, a function is used to show a correct discount calculation. It starts with an original price of $50, then applies a 10% discount by multiplying the price by 0.9. The result is the discounted total cost in dollars. Finally, the function prints this discounted price with a clear label to show the intended result. After defining the helper function correctly, we use it with an input of 100 miles to compute the gallons used. The function converts miles to gallons by dividing the miles driven by 25. It then rounds the result to 2 decimal places. Finally, we print this value, showing the correct use of the function after its definition. This script demonstrates common name error problems in Python and how to fix them. It first shows how a misspelled variable causes a name error, which is caught and printed to emphasize the need for consistent naming. The corrected version then runs properly, calculating a discounted price and displaying the result. The script also illustrates that calling a function before it is defined leads to another name error, which is resolved by defining the function later. Finally, the corrected function is used to convert miles driven into gallons used, reinforcing the importance of correct names and proper order of definitions in Python programs. Type mismatch errors. Type mismatch errors happen when you try to use operations on values that have incompatible types, such as combining text with numbers in Python. For example, adding a currency symbol directly to a numeric value will fail because Python cannot do arithmetic with text and numbers together. Each value in a program has a specific type, and operations only work for certain type combinations. Understanding and respecting these type rules is essential to avoid errors that can interrupt your program. Type mismatches in Python occur when you try to combine or compare values that have incompatible types. For example, comparing a list of scores with a single score, multiplying 2 pieces of text, or subtracting a text-based date from a structured date object will cause errors about unsupported types. This often happens when user input, which is read as text, is used directly in calculations without first converting it to a number. In all these situations, the core issue is that the operation expects certain types but receives something different. To resolve type mismatch errors, first identify what types are involved and what type the operation expects. Once you see the mismatch, you can either convert a value to a compatible type, pick an operation that works with the existing types, or reorganize your data so the types line up. For instance, convert numbers to text when building readable messages, and convert text to numbers before doing calculations. Using this consistent approach makes diagnosing and fixing type mismatches a routine part of debugging. Python code, type mismatch errors. This material introduces common type mismatch errors in Python using simple, beginner-friendly examples. It explains how Python raises errors when you try to use values of the wrong type for a particular operation. The focus is on seeing how Python complains in these situations, and then correcting the problems by using explicit type conversions and choosing operations that match the data types. It also clarifies that no external libraries are needed for this basic demonstration, despite any mention of installing them. In this example, one variable holds a text value that looks like $5 with a dollar sign, and another variable holds the numeric value 10 to represent more dollars. We then indicate that we are trying to add a text value and a number, which are not directly compatible in Python. When the addition is attempted inside a try block, the operation fails because Python cannot add a string and an integer. This mismatch in types causes a type error. In this part of the code, a try except block is used to handle possible type errors. A type error occurs when an operation is attempted on incompatible data types. When this happens, the except block catches the error and prints the error message. This message explains which operand types were not supported, making it easier to understand what went wrong and to debug the code. We start by printing a message that we are showing the correct way to join text and a number. Then we build a new string by combining the word for dollars, a plus sign, and another dollar sign with the numeric value converted into text. Converting the number to text is essential, so both pieces are the same type and can be joined without causing an error. Finally, we print this combined message, which correctly shows the text and number together as one string. We begin by storing the text value 15 in a variable to simulate user input that is still just text. We then show a message explaining that trying to multiply this text by a number is incorrect. Inside a try block, we attempt to multiply the text value by 12. This is designed to fail and produce a type error, because Python cannot perform meaningful arithmetic multiplication between a text value and a number. In this part of the code, we deal with a possible error that happens when trying to multiply a text value by a number. If Python raises a type error because this operation is not supported between those types, we catch that error. We then print the error message so we can see exactly what went wrong and better understand why the operation failed. We first convert the text that represents miles into an integer so we can use it in arithmetic. After this conversion, we can calculate the total number of inches by multiplying the miles by 5,280, the number of feet in a mile, and then by 12, the number of inches in a foot. Finally, we display both the numeric value of the miles and the computed inches to clearly show the result of the conversion. This script shows how type mismatch errors occur in Python and how to fix them using type conversions. It first tries to add a text value that looks like a dollar amount to a number, which fails because Python cannot combine a string and a number directly, and is corrected by converting the number to text so they can be joined. It then tries to multiply a text value that represents miles by a number, which also fails until the text is converted to an integer. After this conversion, the script can correctly compute total inches by multiplying miles by feet per mile and inches per foot. Overall, it highlights that you must use compatible data types when performing operations in Python. In this lecture, you learn to differentiate between syntax, runtime, and logical errors in Python programs. Interpret Python error messages and tracebacks to identify where an error occurred. And fix common beginner mistakes that lead to typical Python errors. In the next lecture, Lecture B, we will go over debugging techniques.
Thank you for your attention. See you all in the next lecture.